Now that we know the law of the unconscious statistician, we can define variance very easily. Okay, so variance of a random variable x is defined as the expectation of square deviation from the mean. Okay, so this x is the random variable and this mu is the expectation of x. Okay, so let's read this way. Expectation value of square of deviation. Deviation means deviation, difference from the mean. Deviation from the mean. Okay, expectation of square deviation from the mean is the variance. Okay, maybe you have heard of this formula for variance. Expectation of x squared minus square of expectation. Right? Actually, this is a kind of theorem derived from this definition. Okay? But I don't recommend using this as a definition because the meaning of variance is very clear in this original definition. Okay? As we have said, it's expectation value of the square deviation from the mean. Okay, that's the meaning of variance. But here, that meaning is gone. Of course, mathematically speaking, they are equivalent, but the meaning is not clear in this formula. For example, because of this definition, we can clearly see that variance cannot be negative, right? This is real number, real number. If squared, it's always non-negative, 0 or positive. And if you take the expectation of positive, non-negative numbers, then it should be non-negative. It can never be negative, right? But if you look at this formula, it's not so clear. Is this always greater than this? Of course, you can prove this because ultimately this is equivalent to the original definition. So of course this is positive or non-negative. But it's not very clear from this formula. Okay, and the square root of variance is called standard deviation. And in statistics, we usually call standard deviation by a special Greek letter called sigma. By the way, this is also sigma. This is uppercase. This is lowercase. Okay. So let's see. In the case of expectation value, if we have x as a random variable and a and b are constants, we have this relationship. Okay. This is easy to derive because just apply the definition. So this is integral a plus bx, probability of dx. And since this is integral, let's just distribute this, x, dx. And this is constant, so you can get this outside the integral. Again, this one also. But this is probability, and we integrate all over the possible values. So this is 1. This is the second axiom of second axiom of the probability measure. And this one is the definition of expectation. So that's why we get this. Similarly, we can calculate the variance according to the definition. Variance of a plus bx. But in this case, we have b squared and variance of x. And you should note that a is gone from here. Okay. Proving this is an exercise. Okay. Now let's define more general quantities. Okay. The first one is the earth moment about the origin. That is where this r is integers, natural numbers, like 1, 2, 3, 4, and so on. So we write it like mu r prime is expectation value of x to the power of r. Okay, so for example, r1 prime, mu r1 prime, mu1 prime is expectation value of x. Mu2 prime is expectation value of x squared, and so on. Easy. Then, similarly, earth moment about the mean. About the mean. Okay. And let's say mu is the expectation value of the random variable. Then mu r is defined as expectation value of x minus mu to the power of r. Okay. So actually, when r is 1, then this is 0, right? Mu. But this is x minus mu, so it's x and mu, but this is mu itself, so it's mu minus mu and 0. And when r is 2, mu2 is this, x minus mu squared, so that's variance of x. Okay, And we can define the third moment about the mean. But yeah, of course, this may give some information, but we actually define a better quantity than this. Before that, let's explain about the standardization of random variables. Okay, let's say mu is the expectation value and sigma is the standard deviation. Okay, then we define a new random variable by x minus mu and divided by sigma. So this new random variable z is called the standardization of x. Okay, why is it called standard? Okay, okay, what's the expectation value of z? So if you apply the definition, but mu and sigma are constants, so we can have this minus mu sigma, but this is mu, so this is 0. So the standardization of x, it has the mean of 0. And what about the variance? Variance of x minus mu sigma. And from a previous exercise, you can see that this is equal to 1 over sigma squared and variance of x. But sigma was the standard deviation, so the variance of x is sigma squared. So the variance of z is 1. Okay? So by standardization, we mean a random variable of mean 0 and standard deviation of 1. Okay? By using this, we define the standardized earth moment. Okay. Standardized earth moment. Okay, which is defined as this expectation of z to the power of r, which is x minus mu sigma to the power of r. All right. And in particular, when r is 3, this is called skewness. And when r is 4, this is called kurtosis. Okay, what do they mean? Okay, suppose we have a density function like this. Okay, and the mean is somewhere here, and the variance, which is the second moment around the mean, represents the width, this spread of distribution. So when this spread is large, the variance is large. When the spread is small like this, so spread is small like this, then the variance is small. Okay. The skewness is the third standardized moment. Standardized third moment, which means, okay, let's write the definition. Probably it's easier to see in that way. Okay, so inside this expectation, this is the power of 3. Okay, so that means depending on the value of x, this value can take either a positive value or negative value. So, and on average, if this skewness takes a positive value on average, that means it has more positive values of this quantity, right? So that means the distribution would look like this, for example. So it will look like this. For example, it has a long tail to the positive side. Okay, so if you calculate the mean of this distribution, it will be somewhere like here, probably. So this will be the mean. Okay, and above this mean, there is a long tail. And below this mean, the tail is not so long. In that case, this quantity, x minus mu divided by sigma to the power of 3, for these values, this will take a huge value. But for these values, compared to these values, they are not so big. So on average, this will be positive. In contrast, some distribution like this, probably the mean is here, the skewness will be negative because it's spread far to the left, negative side of mu. So the skewness in this case would be negative. So the skewness quantifies the bias towards the value greater than mean or less than mean. When it's positive, it has a long tail to the positive side. If it's negative, it has a long tail to the negative side. What about the kurtosis? Oh, of course, if the distribution is symmetric around the mean, if it is completely symmetric, then the skewness should be close to 0. If it's strictly symmetric, then it's exactly 0. Okay. And what about the kurtosis? So can you compare the function between of this and this? So kurtosis is the fourth moment. Okay. Kurtosis is the fourth moment of the standardization. So if you compare these two functions, it will look like this. So y equal to x squared probably looks like this. What about y equal x to the power of 4? It would look like more or less like this. maybe I should use a different color. So that is, this is around 0. This function is closer to 0. But above 1, so here's 1, here's negative 1. Actually, it should be symmetric, but anyway, it will go up very rapidly, a lot faster than x squared. Okay, so that gives you the hint of how this would behave. Okay, so if you look at inside this, if x minus mu is the absolute value of this is greater than sigma, then the value of this to the power of 4 would be very large. It will increase very rapidly. On the other hand, if this difference is smaller than sigma, that means this inside this is less than 1, then it is close to 0. So this measures how far the distribution is spread beyond the standard deviation. Okay, let's see. So that means if you have a distribution like this, probably the kurtosis is not so big. But if you have a distribution like this, it's not a good example. I don't know. The kurtosis should be bigger. Yeah, it's more spread to the far side of the distribution.